Well, hello, guys. Today we're going to be presenting about recursion and dynamic programming.
Very cool.
Very
Thanks
cool.
for introduction, Kevin.
And first off, we'll be starting off with recursion. Kegan's going to be taking away.
So recursion is pretty much just referring to a function that calls itself, and there are lots of variations of it, but that's the base form that we're going to be talking about. A function that calls itself. This is often useful when a problem that we're trying to solve, as computer scientists, is more easily solved when broken down into easier problems. So we take the big problem, we break it down into one or more easier problems, and then we solve those. And we can do that through recursion, the function calling itself.
Are we ready to move on?
Yeah. So often iteration is taught before recursion in most CS classes, including the one in the school. Iteration, I'm sure all of you are familiar with, is linear. There's only, it's one thing happening at a time in a line, typically using a for or while loop. It's very easy on the stack. The stack, I don't know if you guys talked about this last time, but the stack basically stores the running state of the program. However, for some problems, this can be quite difficult to implement. Not impossible, but quite difficult. And a solution to that is recursion. You can recur linearly, where the function only calls itself once, but it can also have a tree structure, where one function call will result in, two more function calls, each of which result in two more, creating an exponentially expanding tree. The main problem with recursion is that it's very hard on the stack and can create a stack overflow if you try to go too deep into the tree.
So
if the depth gets too large.
I'm just going to mention something just to make this more clear.
Yeah.
Basically, since we talked about a tree and how it exponentially gets larger and larger, you guys know exponential growth. The more you get, you'll get to a certain point where it's too much for the computer's memory and you'll get a stack overflow.
Mm-hmm. Yeah. The nice thing about recursion, though, is that it's very, very intuitive for some problems. And it's often inefficient to just do one line, because you could, with one function call at the end, because then that's basically just a loop. So let's go on to I forgot what the next slide is. Yeah. So each call of the function gets placed on the stack, and recursion is generally the same as a depth-first search, but handled by the computer. So you don't have to deal with a lot of the complicated aspects of that.
So if you guys don't know what depth-first search is, there'll be an algorithm that will be implementing recursion that will be learning in a couple lessons about graphs and trees, which are a complex data structure that are very important in computer science.
Very common. Trees are quite widely used.
All right.
Another very, very important feature of recursion is something called a base case. So you can obviously break down the big problem into smaller problems, but eventually you have to stop splitting it. Otherwise, you'll keep going on forever. The point at which you stop splitting it, sort of like the point on the tree with no child nodes, is called the base case. These are trivial questions that you don't need another function call in order to solve. And we will look at the hallmark example of this now.
So I have an example.
Fibonacci. Yay. Everybody loves it. Oh, wait. Let me delete this. You guys don't look at this. Whoa, that's not quite what I meant to do.
Tell me when you're ready.
Yeah.
First, we gotta pre-code this. All right, Kegan.
Okay, so you can switch back to it.
All right.
So I'm gonna make a function called.
Oh yeah, and I'm just gonna mention something before you continue, Kegan.
Yeah.
Fibonacci, if you guys don't know what the Fibonacci sequence is, it's a sequence in mathematics that is that's very recursive. So when you start, so the first number is 0, and then the next number is 1, number is 1. And to get the next number, you take the two previous numbers and add them together. And that's why it's recursive. It's because you need the values of the numbers previous to it to be able to get the answer.
How do I do this? Just a second. I'm having a bit of trouble setting this up.
Yeah, all right.
Okay, I think I'm good. All right, so the nice thing about, I just have a little bit of stuff in the main function here that'll call it and print out a nice thing. So the thing about Fibonacci is let me clear this.
So
okay. The thing about Fibonacci is you take the nth element is the sum of the previous two elements. So one common way of doing it is to iterate through the elements and keep track of what the previous two were. Tian, get out of here. Okay, whatever. It doesn't matter. It doesn't matter. So a nice way to do this would be return value minus 1 plus value. Right. So now I can just return the previous two Fibonacci numbers summed together. And I'm actually going to do it like this instead. So, however, this is just going to keep on going infinitely because there are no base cases. So I can just implement those real quickly. If the value is 0, fine, whatever. We'll do it like this. No. I'll return 0.
In the Fibonacci sequence, if the 0th number in the Fibonacci sequence is 0, the first number is 1.
I mean, I was using 0 as 1 and then 2 as 1, but whatever.
Yeah.
Whatever.
It
Anyway, it doesn't really matter.
1.
Sure.
That's what's important.
Okay, so now I have base cases. So it'll keep going deeper and deeper into the tree until it hits a 0 or a 1, at which point it'll then stop going any deeper and return that value. So if I try, oh wait, small brain. Okay.
Oh yeah, and if you guys didn't know what a long is, it's just a very long integer. That's the point.
Because Fibonacci numbers get pretty big pretty quick, so it's just a longer.
Yeah. Python doesn't have any restrictions on its integers. It will just continuously grow and get more and use more memory. But in C++, we need to numbers will have a cap on the memory that they're allowed to have. So you need to have a long number.
So this is pretty much it. And as you can see, this is a very, very small function. And this does the entire Fibonacci sequence. So that's sort of why we picked it. It's a very intuitive coding example. However, it's extremely inefficient. If I try running this on bigger numbers, let's try something like 30. It did that pretty quickly. Okay. What if I want to do something like 100? Well, I'm going to wait. And I'm going to wait. I've got a separate implementation of it right here in my other tab that will allow me to watch its progress. So it'll let me know. This is just the same function, but with a bit of extra stuff. And this will show where it is in the process. So it gets stuck around 40, and it slows down so much because the tree is getting so wide that the processor can't handle it. And this is a problem. And I believe Kevin will now talk about the solution to this problem.
Yeah, so we'll be going into dynamic programming. And also, if you guys didn't understand the types of calls that are happening in recursion, I think you'll get I'll have a great visual representation for that. So let's get back to our presentation. So recursion, so an optimization over plain recursion is dynamic programming. So for some of the calls in the trees, we're just repeating, like computing fib1 over and over and over again, and we don't need to do that. So instead of repeating these calls, we can optimize this by storing the results in an array, for example. So we don't have to recompute these, and this makes us that the optimization reduces the time complexity from being an exponential growth to a polynomial growth. So polynomial would be probably like x squared. If you guys didn't know, I think we went over big O notation. Exponential will grow a lot larger than polynomial. So let's take a look at this. All right, this is a great example of a Fibonacci tree. Like just example. So we'll start off. All right, I want to know the fourth Fibonacci number, and so then what do I need to do to know the fourth Fibonacci number? I need to know the third and the second number. All right, how do I know the second number? I need to know the first and the zeroth number, which we do now. So then that returns, right? But then, as you can see, we repeat these calls for the zeroth Fibonacci number, and also the second Fibonacci number. So with dynamic programming, we can essentially remove all of these calls, 1, 2, 3, 4, 4 calls from this from the tree, and it makes it a lot more efficient. So let's get into two of the ways that you're going to see this implemented in your code. So we have the first method. This is an iterative method that you'd be able to use dynamic programming. So this is called tabulation, and it's and some people usually just commonly call it dynamic programming. But I'm just going to split these up into tabulation and memoization. These are both types of dynamic programming. So it's bottom up. So what I mean by bottom up is that it starts at the bottom of the tree and goes up. So we first start solving these solutions from the smallest input. So we're going to compute fib0 first, and then fib1, and then we're going to keep going linearly across an array and get each entry. So then you can basically use these previous entries in the array to compute the later entries, and it's done iteratively. The other way, which is a recursive way, and just an add-on to our previous recursive code, is memoization, which is top down. So basically, we start off at the top, right, and we go down and we look at 3. I want to compute 3 and 2, and then if we're computing 2 first, we compute f1 and f0 first, and then since we've already computed them, as we go to f3, we've already computed f2, so we can scrap this and we can scrap this. So that's how that works. So it's the same as recursive solution. It's just that we're going to be storing values in an external array, and every time we want to figure out the answer, we're going to check that array if that answer is being computed. So I've got some great diagrams to show you. So first of all, this is Microsoft, my fabulous art skills in Microsoft Paint. So here's an array, and a great example. So we start off with the 0 and the 1, all right, and the 1. So we go iteratively from across each index, and the next at index 3, if we want to compute it, we just take the first 2. So 1 plus 1 is 2, right? The memoization is more a recursive solution. So we're going to start at 4, and then we're going to look. Oh, I want to compute what fib2 and 3, and as I explained before, as we go, so we start off on the right side, we can compute fib2, and then once we go down here, we already seen that we've already computed the fib2, so then we can just skip these computations. So let's get into some code examples. All right, some more code examples. So I've already pre-coded this because it's quite a lot, so I'll just be going over it with my cursor. You guys can see that. I think it will help you guys a lot. All right, so the first part is tabulation, right? So I have a lookup table right over here, and I'm just initializing this just so that I'll have enough space. And we know that at the 0th index, Fibonacci is going to be 0, and at the first index, it's going to be 1. So these are our base cases. And then we're just going to be using a for loop, starting at number 2 and going to n, and basically filling out each entry. And we continue to do so, and this is just a print statement. And eventually, we're going to return the nth value, and that's what we want to do. All right. And I'll just go show you guys. I'll show this in action. It's gonna take a little bit of time. All right, here. So we already know that index 0 is 0, index 1 is 1. All right, but index 2 is gonna be 0 plus 1. So then we result in 1. Index 3 is gonna be this value 1 plus like the last two numbers. So then 1 plus 1, 2. This is gonna be 1 plus 2, which is 3. 3 plus 5 is 8. 5 plus 8 is 13. I think you guys will be able to understand that. And personally, when I get the chance to, I just feel like this method is a lot more intuitive because I really like to do things iteratively. But if you guys are more like to do things recursively, I'll show you the next implementation. So here's the memoization. So right here we have a lookup table. I just initialized it with 1,000, just like so it has enough memory. So then I've also initialized every value to -1 to basically for us to be able to check if the value at that index, if that fib number has not been computed. So the only difference that we have is that every time we call like Fibonacci memoization, we just at least take a look at the lookup table if the value isn't there, if the value is not computed. If it's not computed, then we do whatever we were going to do to compute the value. Otherwise, we can just retrieve this value and then just return this value. So that's the main what is it again? The main optimization. As you can see, my code is a little bit different than Kegan's for the base cases. I already know that every number that's smaller than or equal to 1 for the index is going to be equal to its value because index 0 is equal to 0, index 1 is equal to 1. So if I run this code though, I've also have some print statements just to show you guys how it works. All right, so we first ask, oh, what's fib number 9? Oh, fib number 9 is fib 7 plus fib 8. All right, and then let's go to fib number 8. All right, fib 8 is fib 6 plus fib 7. All right, and then what is fib number 7? And as you guys can see, I keep asking this question until we get to the smallest cases where fib are base cases. Fib 1 is equal to 1, fib 0 is equal to 0. And then, since we've already computed these values, we can just retrieve these values. Every time we start computing, we can just save so much time. Like when we're trying to retrieve fib 4 in one of these numbers, we can just retrieve it, and it just cuts our tree and the number of computations we need to do by so much. Yeah. So just as a wrap up, so memoization, all you need to do in your recursive code is just add an if statement to check if that value has been computed. And then when you want to compute it and when you have computed it, make sure you store it as well in your lookup table. And for tabulation, it's an iterative process. It's an iterative process where you basically fill in every single value in the array. You start off at the start, and then you go each index until you get to the value n, which is the number you want to compute, and then you're able to return it. All right, but wait.
So you might be thinking, but Kegan, can't I just use iteration in all of my problems? Because one of the things that we have been talking about is how they're kind of similar, and often iteration is actually better because it doesn't have to expand exponentially. Although there is memoization, which is also good. But anyway, there are a few examples where just straight recursion is in fact, again, generally the best way to do it. And that is quicksort. You may have heard of quicksort. It is one of the best sorts. I'm not going to get into an argument about what the best sort is, but it's certainly up there. And it uses recursion. So you want to go to the next slide? So it works by, oh, it's in the middle of I don't know. Why is it starting in the GIF? The GIF is okay. Whatever. The animation is starting in the middle, so let's just wait a second for it to start over, and then I'll explain what it's doing. It basically it takes a random pivot shown by the black square and an array, and it'll sort the array so that Kevin, can you go back one so that the thing on the right isn't shown? It's kind of distracting. Thank you. And then it'll sort the array so that all elements on one half of the, or like one side of the array, are less than the pivot, and all elements on the other side are greater than the pivot. Sort of making sure that the left side is smaller than the right side. And then it'll resort each half. So it's starting over here. First it picks a random pivot, in this case 3. And then it looks at 6 and 4, and it'll go until it finds 2 that are on the wrong side. So 2 is too big, and 2 is too small, and 6 is too big, so it swaps them. And then it keeps going. In this case, it stops on 5 because 5 shouldn't be there, but 7 and 8 should be, and then it swaps the 5 and the 1. And then once it's done, like, it's not really sorting, but once it's done ordering the list, it'll split it into 2 sublists, and it'll sort those. See, now it's comparing 2 and 1. That just requires one operation to switch. And now that whole part is sorted. So then it'll run the sort on the remaining 5 numbers.
Yeah, all right. I think.
And on the right is an example of it working. And I also have a coded example in the REPL once the animation's finished.
All right. But one thing though to note is that dynamic programming is especially efficient if we're trying to compute like values, right? If we need like Fibonacci sequence, we're trying to compute values. That's why it works so efficiently that you can cache and you can make sure that you're not repeating some of the work that you've already done. That's the main point of it. Well, in sorting mainly is efficient because we divide and conquer. That's what a lot of sorting algorithms do, as you can see. So basically, a lot of sorting algorithms will divide it into 2 parts, and then keep dividing it into parts. That's merge sort. And then what people figured out, it's very efficient to sort small, like 2 halves instead of one big array. And that's I think Chapman will teach you guys that in grade 12 computer science. If you guys are interested in that, he'll go over a small lesson he'll go over sorting algorithms, but I don't think, for the most part, it's not really too important for you guys to know because a lot of sorting algorithms are already implemented. It's just a cool thing to understand.
Right. Hey, yeah, you want to switch to the REPL, and then I will do a.
All right, Kegan.
Okay.
This is very satisfying. Not gonna lie.
It is. Sorting algorithms are so fun to watch. All right, so here is. Here's a bunch of numbers, and I've just coded it to accept a series of numbers and then a non-number. And if I run it, bam, super speedy, and it's done. It divides and conquers, so it's got the big array, and then it semi-sorts it into smaller arrays, and so on.